Okay, next we have a speaker from computer science at the University of Glasgow, Dr. Fani Deligianni. Who will speak to us about clinical support systems. And I will just give you this mic so it's easier.
Thank you. Thanks for the invitation. So change a bit the title, but yes, it's about explainable privacy reserved in emotional analysis in healthcare application. So we know that human motion is an important index in several disorders such as neurological diseases, mental disorders. It's important to in order to predict and prevent falls in elderly. It's also obviously important in sports and orthopedics, and it is used in human-computer interaction, and also the studies that they show that relates to cognitive workload. So we have done two experiments where we use multimodal resources in order to estimate human motion. And here, for example, you see a subject where has been asked to adapt their gait based on a musical tone. So if we play this again, then what you can see that at some parts it's going faster, and once the tone changes, then it has to adapt to a slower or to even faster pace. So we use here a near sensor, which is an accelerometer. Effectively, we have the video camera at the same time we record EEG. And the idea is whether we can predict the intention of the person to adapt the gait either to a slower or to a faster pace. So effectively, with the EEG acquisition, we filter the signal to remove motions, and then with epoch based on the gait characteristics, we have data from the gait, and we use regularized conversational patterns in order to be able to extract relevant EEG features. And that gives us a relatively simple way to predict whether the person intends to go faster or intends to go slower. So following this work, we've seen a lot of application of deep neural networks in human motion analysis. So we know that we can extract pose relatively accurate. We can extract cloud of points and shape. We can do that online and so on. And this was some work we did where actually we used transfer learning in order to improve the ability to detect abnormalities with the RGB cameras or surface EEG sensors by transferring knowledge from mock-up systems, which are considered the gold standard in human motion analysis. So now the question is how we use all this knowledge when it comes to healthcare applications, because there's several criteria that we should take into account, which they have to do with the privacy of the data, they have to do with the interpretability and the transparency of the model, they have to do with the technical robustness on whether we can estimate confidence intervals, and so on. So how it goes yet? So let's see an example here of human motion analysis in affect recognition. So we see here visual characters walking, and each of them represents a different affect. So even a human would be relatively difficult to realize which is the effect once we don't have the labels. So in healthcare, we have subtle variations that we need to detect. And we also need to consider, as I said, that we would like to apply this in home environments and of the patient. Therefore, privacy is important as well as explainability. We have lack of label data, so compared to computer vision applications with thousands and millions of label data, here you have few tenths of data, you have imbalanced class distribution because of the fact that some of the classes is going to be more rare. And you need to estimate bias. You need to make sure that this is clinically useful. You have to prove that it's better than existing systems. And for this reason, we need also uncertainty estimation. But here I would focus mostly on some work we've done for explainability and privacy. So I show you here mock-up data. And we see here again the 4 different effects in those data. The younger have been neutral and sad. So one way to go around in terms of privacy, to preserve the privacy of the subject, is to use to disentangle effects or abnormalities from biometrics. And here we use a combination of autoencoder network where we try to optimize at the same time the reconstruction loss, which typically comes with autoencoder, as well as the cross reconstruction loss, which allows to estimate latent variables of the pattern of interest. So we know that human motion analysis has been used for personal identification. So we can see that we can disentangle subject identity. But we are really interested of our pattern of interest here is affect. So what we are trying to disentangle is either happiness, sadness, or a neutral feeling. So we observed by disentangle the effects from the biometrics, we would be able to improve the performance, and that we compare that with more shallow models. And we also will compare it with classical convolutional neural network. And we did that while at the same time we preserve the privacy of the subjects. And we measure that by trying to classify here the subject identity, and we observe that it is reduced with autoencoder structure. Once we present this to clinicians, it's very important to have a way to interpret and to explain the results. And for this reason, we use gradient visualization techniques, we use BRACAM, in order to find the attributions related to the decision of the model. So here what we can see is that we have strong changes in activation around heel stride, even for lower body. And we have activations in upper body through also the arms of the subjects. So the shortcomings of these methods was that it was difficult to generalize to new subjects. And given the fact that we don't have thousands or millions of pictures, we decided to use synthetic data and try to synthesize time series data. And so we went one step ahead with GANs in order to give us the ability to approximate complex distributions. And we also used attention in order to be able to better learn the temporary relationships in our signal. And we also wanted to do that to do it online, to do the human motion synthesis online. Furthermore, we wanted to use this framework and evaluate this framework based on the classification performance. So we wanted to use it as a data augmentation approach. So effectively, we used end-to-end training with Wasserstein GANs, and this implies that we have a critic which returns a probability of whether sample is fake or real. And here you can see also that we have a control vector which allows us to control the type of effect or the type of activity that the network will produce. So going to the next step, here it was to design the network. We see here the encoder network. We see here as an input a seed motion and the control vector. And also you can see that part of the encoder network, as well as the decoder network, which mirrors the encoder, is an attention mechanism. So the message here is that we can combine convolutions with attention mechanism in order to benefit both from the efficiency of the local filters that the convolution mechanism provides, as well to allow us to model more distance relationship in our data based on the attention. So the way to train our generator here was by combining the classical GANs loss with three other losses, which is the loss from the skeleton, which just physically constrain the bone length. We had here a loss, a blending loss, which allows the motion to be smooth. And we have also a classifier loss, which relates to the ability to control which type of motion the network generates. And similarly, for the critic network, we again have a loss based on the difference between real and fake, as well as interpolation term. And what we found here is that the attention mechanism, it would allow indeed to produce better human motion patterns, especially after the first few seconds. And we compare this, you see here the ground truth, we also use it as a reference, an LSTM neural network, which after a point it starts converges towards to a mean. So that's why you see that the motion is slowing down and it's not being able to effectively keep the online autoregressive nature of the human motion. When we evaluated this approach with relation to the ability to synthesize data, we saw that it did perform better than the synthetic data produced from LSTM. And it was able to perform well even with 10% of the real data. But it didn't improve with relation to the performance. You could already get with the real data. Pointing out that synthesizing time series data is quite challenging still. So I would like to acknowledge here both the contribution of my group and my students, but also my sponsors, including EPSRC, the Royal Society, MRC, Canon, and as well as collaborators from NHS, Lanarkshire, and Oldham Jubilee. Thank you a lot.
Okay, there any questions from the room? Yeah, very much. Oh, jump over.
Hi, interesting talk. Thank you. Can you hear me?
A little bit.
Hey,
That's better.
I was wondering, where did you base the reference for the latest? You mentioned emotions such as
Yeah.
happy,
So
angry.
we use the public data set, and this is based on actors that indicate specific emotions.
Can you really generalize these kind of patterns? I mean, every person has a distinct gaze pattern, or for example, I might be different compared to someone else when I'm walking in the
Yes, you're right. That's a difficult problem to solve, and that's why it's far easier to produce better results within subjects rather than when you are a new subject. But you would expect that some emotions they do have similar patterns. If someone is sad, for example, it's quite likely he will walk more slowly, and maybe his posture will bend or hair posture. So we do expect from some basic emotions to see some similarities across.
Thank you.
Okay, are there any other questions for this? Okay, well, thanks again, Fani, for your talk. They're almost out of time. Just a last talk here.